Welcome back. So in the last video we derived the full expression for the force that you have in atom-light interaction, and today we would like to discuss this result and so discuss the properties of this force and also give some physical intuition and physical meaning to the formulas that we have derived. So this is a summary of what we discussed in the last video. So we derived the two contributions for the force. One is the dipole force and the other is the radiation pressure force. And those are proportional to the two components of the block vector, uv, that describe the component of the atomic dipole that oscillates in phase with electric field, that is the one indicated in red in this expression, so the component that is proportional to u stat, and the other is the component that oscillates 90 degrees out of phase with respect to the field, that is indicated here in blue. And before discussing fully and in detail these two forces in a separate way, let me discuss a little bit more about this in phase and out of phase contribution to the electric dipole. And for instance, let me draw what is the dependence of these two components, U and V, on the laser parameters and specifically on the detuning. So I will sketch a drawing now, and let me draw some axes. So here we'll plot the U and V components as a function of delta. So starting from the U component, so the U component you can see here that is 0 for delta equals 0, and then it is an odd function of the detuning. So in particular it is negative for negative values, and it is positive for positive values of delta. And so the shape of this, so the graph of this function is the following. So this is stationary U. And in particular, we can observe that at large detuning, so when delta is much larger than omega and gamma, so basically U stationary goes to 0 as 1 over delta. And so this is the behavior of these large detuning tails. Instead, V as the expression of a Lorentzian function of the tuning, so it is 1 over delta square plus some constant term, and so its graph will be a function like this. So this is stationary V, and so this is maximum on resonance, so for zero detuning, and for large detuning, so its asymptotic behavior is that of a Lorentzian function, so it goes to 0 as 1 over delta square. And keep that in mind because these two different asymptotic behavior will be very important then for application. So 1 over delta square. So the V component goes to 0 at large detuning much faster than the U component. So let me say that these two components are associated with two different properties, two different characters of atom-light interaction. So specifically, so you can see here that V component of electric dipole that is 90 degrees out of phase with respect to the electric field, so its dependence on the tuning is the characteristic dependence of an absorption process. So it is maximum on resonance, and then it goes to 0 with the Lorentzian function that we already discussed in the last lectures. So I will make this connection to absorption more clear in a few minutes. The other component, U, is oscillating in phase, is describing the component of electric dipole that oscillates in phase with electric field, and this instead connected to dispersive properties of atom-light interaction. And these two terms, absorption and dispersion, are connected with effect of the atoms on the properties of light. And let me just remind you something that you should know, but anyway, I will make this point more explicit because it is a general remark that is important for understanding the properties of this interaction. So what have we seen? We have seen that the electric dipole is basically, at least for weak values of omega, so in the low saturation regime, D is basically proportional to the Rabi frequency, and so this is proportional to the electric field. And we can see that, for example, from these expressions, because being far from saturation basically means that we can neglect the omega term at the denominator. So this is the limit of small values of omega. And so this in turn implies that both U and V are proportional to omega, and in turn they are both proportional to the electric field. So the electric dipole is proportional to electric field. This is the regime of linear interaction, so when saturation is not important. We can express this proportionality by introducing the atomic polarizability alpha. And the atomic polarizability is usually expressed as a complex function with a real and imaginary part. And of course, the complex nature of the atomic polarizability emerges when one writes both the electric field and the electric dipole in an exponential form, so something like that. So E can be written as some amplitude times e to the minus I omega t. And let's consider, for the sake of simplicity, a plane wave, for example, something like e to the minus I omega t minus kx, and the electric dipole, of course, will be alpha times E, so alpha times the amplitude times e to the minus I omega t minus kx. And of course, the real component of a polarizability is associated to the U component of a block vector. So in particular, so we will have here a minus sign, and the imaginary part instead is connected with a 90-degree out of phase contribution of electric dipole, and this will be proportional to V. And of course, this is straightforward, and it comes from the expression of D and E that we gave before. And this sign minus comes from this expression, so you have a minus sign here, so the real part of atomic polarizability is minus U, and the 2 minus sign in front of V will cancel, and so V will be equal to the imaginary part of the polarizability. And of course, sorry, there will be some constants in between, but I would not like to discuss those in full detail, just give you the flavor, so this will be, generally speaking, proportional. And so what is the meaning of a real and an imaginary component of the atomic polarizability? And so you have already done this calculation, but let me recall it. So let's consider a gas of atoms, and this gas is made of many particles. Each of these particles will be described by some atomic polarizability alpha, and the collective properties of these atoms are described with a macroscopic quantity that you introduce in optics, and this is the index of refraction. And the index of refraction is connected to the electric susceptibility chi, where chi in turn is proportional to alpha, with some proportionality constant let's call it gamma, that I would not like to review now. So this gamma will contain the density of particles, some fundamental constants, and so on. This is not important for what I would like to say. And then you can expand this expression and you will get, in the limit of small densities, for example, 1 plus gamma half times alpha. Alpha has some real and some complex quantity, and so this means that we will have some real and imaginary quantity of the index of refraction. And so now, when we consider the propagation of the electric field that has the expression written above, we can, for example, rewrite the k vector as, so k is omega divided by c when the wave travels in vacuum, but now we are considering some wave that is propagating in the sample. And then, so we need to consider here the velocity of propagation v, and this v is given in terms of an index of refraction by, so this omega t minus omega v is c divided by n, and so we have the following, and this can be rewritten as an amplitude times e to the minus I times omega t minus omega t divided by c, real part of index of refraction, times x plus I, and let me free some space. Sorry, this is minus I omega over c, imaginary part of index of refraction, times x. And so last passage, this will be epsilon times e to the minus I omega t minus omega over c n r x, times e to the I times I is minus 1, and so you have minus omega divided by c and I times x. So what we get from that? So we see that the real part of the atomic polarizability that is connected with a u component of a block vector basically enters the real part of the index of refraction, and in turn determines a different velocity of propagation inside the atomic medium. And so this effect is what we call as a dispersion. So the velocity of a wave will change. And instead, the imaginary part of the polarizability that is connected with a v component of a block vector is instead connected with the imaginary part of the index of refraction, and in turn, so this determines a kind of exponential decay of the amplitude of a wave as the wave is traveling across the sample. And so this attenuation is connected with absorption of light. So this is something that you should already have studied, but let me say one final thing about these two processes of absorption and dispersion, or let's say it better, these two different characters of atom-light interaction. So, and this regards the dependence on the detuning, because of course, when you have absorption, and so we are referring here to the blue curve, so to the imaginary part of atomic polarizability, so this is maximum on resonance. So in the resonant regime of atom-light interaction, absorption is dominant over dispersion. While in the case of large detuning, so at large values of delta, because of a different dependence, asymptotic dependence on delta, that is 1 over delta for the dispersion and 1 over delta square for the absorption, so at large detuning, so the interaction acquires a more dispersive character. So basically, absorption is important for small detuning, and instead dispersion is more important for large detunings. So this will also mean that depending on the detuning, the two contributions of the force, that are the dipole force or the radiation pressure force, will be one more important than the other. And so we will study the different applications of these two contributions to the force in the two different regimes. So in the rest of this video, I will just focus on one of the two, and we will start with considering the properties of radiation pressure. Okay, so to discuss the properties of radiation pressure force, let's consider the simplest case in which you can have this radiation pressure in action. So let's consider an atom at rest, for simplicity, so zero velocity, that is illuminated with just one monochromatic plane wave. So we have a frequency omega and with vector k. And so we can write the electric field associated to this wave as some polarization vector E, amplitude epsilon, times the cosine of omega t minus k dot r. And let's apply the expression for the force we have derived previously to this specific case. That is the simplest case one could think of. And so the expression of the force, let me take it back, was the following. And now we can connect this expression for the electric field with notations we have used previously, and so we can recognize that what we call phi, so the phase of electric field, the specially dependent phase of electric field here can be written quite simply as only minus k dot r. And since we have just a plane wave, so the gradient of Rabi frequency that is proportional to the gradient of the amplitude of the field is equal to 0. So this means that dipole force in this case is equal to 0, because the dipole force is non-zero only when you have some gradient of the amplitude of the field. While in a plane wave the intensity is uniform, and so you don't have this contribution here. Okay, so we are left only with a radiation pressure force, and the radiation pressure force in this case is different from 0, because we have a non-zero gradient of a phase of a field. And the gradient phi can be written quite easily, and this is given by the gradient of minus the gradient of k dot r. The gradient is respect to the coordinate r, and so this of course will be minus k. So now let's write the dissipative force or radiation pressure force in its complete form as minus h bar omega. The gradient of a phase is minus k, so this will be plus k divided by 2 times the v component of a block vector. And so we can use this expression. Okay, so this is the radiation pressure force from a single plane wave that interacts with the atom. And let me rewrite just with some cosmetic corrections. Let me isolate here the term h bar k. Then we have gamma half, and then we have omega square half divided by delta square plus gamma square divided by 4 plus omega square half. And before looking at some properties of this expression, so let me give you an alternative derivation of this formula based on a different point of view. So instead of starting from the general expression for the full radiative force, let us consider what happens from a more on a more physical ground. So let's see what this alternative derivation is. And this is based on what we have already discussed. So the fact that radiation pressure basically is connected with the absorptive properties of atom-light interaction. And so if you have a photon with a momentum h bar k, and this photon is absorbed by the atom, of course, after the absorption, the momentum of the photon should be gained by the atom that will recoil with a recoil momentum h bar k. And so since you have a transfer of momentum, and if you have a transfer of momentum delta p in the unit of time delta t, of course you will have a force, and the force will be given by delta p divided by delta t. And this can be written as h bar k, that is the momentum of a single photon, times the number of photons delta n absorbed that are absorbed in a time delta t. So how can we write this last expression? So this last quantity can be written in the following way. That might seem counterintuitive, but let me first write it and then I will try to convince you that this is the right way to express it. So this delta n abs divided by delta t can be written as gamma, that is the probability of spontaneous emission per unit of time, times rho EE. Rho EE is the population of excited state. So this can be counterintuitive. So why the number of absorbed photons is connected to the population of excited state? So one could think that the probability of absorption should be connected with the population of a lower state. So because, of course, only if the atom is in the ground state, so the atom can absorb photons and go to the excited state and gain this momentum h bar k. So this is counterintuitive because the quantity that is written here is basically the number of photons that are emitted by spontaneous emission in the unit of time. And so why do you have here spontaneous emission instead of absorption? And this makes sense if one thinks to what happens in terms of elementary processes. And let me try to convince you about that. And first, let's see what happens if you have a process of absorption followed by a stimulated emission. So in this case, if you have the absorption event, of course, the atom will gain a momentum h bar k, because the atom will subtract one photon from the laser field. But then, during the stimulated emission, the atom will give this photon back to the laser field, and so it will recoil in the opposite direction. So during the stimulated emission event, it will recoil, losing the momentum h bar k that it gained during the absorption. So in average, if you have absorption and stimulated emission cycle, so the momentum transfer from the laser to the atom is equal to 0. And so basically, this does not contribute to the force. So in some sense, when you consider the average process, you take a photon and then you give a photon back. You take a photon and you give a photon back and nothing changes in average. But the situation is different when you consider now spontaneous emission, because in the process of absorption followed by a spontaneous emission event, now the atom absorbing a photon will of course recoil in the direction of a laser photon, so with h bar k. But then In the spontaneous emission event, so the photon will be emitted in a random direction, and so the photon will recoil in a different direction, h bar, with momentum change h bar k prime, where this k prime is equal in modulus to k, but with a random direction. And of course, since this direction is random now, so the average contribution of spontaneous emission to the change in momentum is equal to 0, and so in average, in this process, the momentum transfer is indeed h bar k. So you see here that spontaneous emission is fundamental in order to have radiation pressure, because spontaneous emission is that process which removes photons from the laser field and will bring these photons to the environment. So, and this is the right quantity that has to be considered here. So the number of spontaneously emitted photons is indeed the number of photons that you have removed from the laser field. So this is why I should put this gamma rho EE term in this expression. And so now let's go back to our expression for the force. This is an alternative derivation of it. And of course, now we can substitute here rho EE that we know very well. And from what we discussed in the lecture devoted to the optical block equations, we wrote what was the solution of rho EE in the stationary state, and this solution is indeed, can be written indeed in the same form. So this is 1/2 omega square divided by 2 divided by delta square plus gamma square over 4 plus omega square divided by 2. And so we arrive to the same expression that we have derived previously with a full derivation of a force that was based on the evaluation of atomic dipole, that we have derived here in an independent way by thinking to what happens in a microscopic process of absorption of photons. But this is a kind of picture that has a lot of physical meaning. So we can think to radiation pressure as that force which comes from momentum conservation applied to cycles of absorption and spontaneous emission of light. Okay, so now we can conclude by just commenting this expression. So let's, for example, see what happens when you change the parameters of atom-light interaction. So we have already discussed the dependence of this force on the detuning, and let me write again that this is a Lorentzian function. So the force is maximum on resonance, and the line width is given by the saturated line width gamma s that we introduced in a previous lecture, and this is given by gamma times the square root of 1 plus s, where s is the saturation parameter. And this comes from, we have already seen that, and this will also be useful in the next lectures in a different way. So we can rewrite this as h bar k times gamma half times s divided by 1 plus s times 1 divided 1 plus delta, 2 delta divided by gamma square. Not gamma, but gamma s, where the saturation parameter was defined as 2 times the Rabi frequency divided by gamma square. We have already seen all of that. And I'm writing that in this way because this is more convenient to understand the dependence of the force on the intensity, so on the saturation parameter. So I recall that this saturation parameter is proportional to the intensity of light, so it can be written in a kind of general way as the intensity of light divided a saturation intensity, that is the typical intensity scale after which saturation effects in the transition become apparent. And so as a function of the tuning, and let's suppose, for example, to consider, as a function of S, and let's suppose to consider the resonant case, so the tuning is equal to 0, this force is, of course, 0 when the intensity is equal to 0. Then for small value of S, it increases linearly with S. So in the non-saturated regime where we can neglect this S as the denominator. And then it increases with a saturation character. So when the S is much larger than 1, so the force reaches an asymptotic value. And this asymptotic value has a kind of simple expression. So this maximum value of force is given by h bar k time gamma divided by 2. And this, of course, is the limit in which S is much larger than 1, and so you can neglect the 1 at the denominator in this expression. So this is an important character of the radiation pressure. So it has a saturation value at large intensity. So we cannot scatter the number of photons that we want. So because in the saturation regime for large intensities, so the typical time associated to a cycle of absorption and spontaneous emission is given by gamma half. So gamma will limit the rate at which you can absorb and then re-emit photons by spontaneous emission. So these are the general characters of a spontaneous force or radiation pressure force. And we've also discussed this alternative derivation in terms of the absorption of photons, and we have seen how we can count them in the proper way by taking into account the process of spontaneous emission. And as a last thing, let me just give you some numbers, just to give you an idea of the value that this force can reach. And for example, let's consider an atom like rubidium. So I have the values for 87 rubidium, and for which gamma is, we know, gamma in rubidium is 2 pi times 6 megahertz. So the wavelength in rubidium is 780 nanometers. And so if you take these parameters and you evaluate the maximum value of force, that is h bar k times gamma over 2 in the regime of saturation, or if you want, h over lambda gamma divided by 2, the value that you get is 1.6 times 10 to minus 20 Newton. And of course, this is a small force, but also the atom is a very light object. So it makes sense to evaluate the acceleration that a rubidium atom has when it is pushed with this force. So if we evaluate the acceleration as this force over the mass of a rubidium atom, the answer is that acceleration is 1.1 times 10 to the 5 meters per second square. So the force is tiny, but acceleration is huge. So this acceleration is on the order of 10 to the 4 g. And this huge acceleration is the reason why laser cooling works so well. So we will see, starting in 2 lectures from now, that we can use radiation pressure in the most common laser cooling protocols to reduce the velocity of a gas of atoms from hundreds of meters per second to approximately 0 in a time of just a few milliseconds. And this will correspond to cooling the temperature of a gas from hundreds of Kelvin to a temperature of microkelvin or even less than that. But this will be the topic of next lectures. So this is basically everything about the radiation pressure force, or at least about the average value of radiation pressure force. So in the next video, I will consider the fluctuations of radiation pressure that will be very important for discussing the limits of laser cooling, and then we will discuss the second force that we have introduced today, that is the dipole force. Okay, so thank you for watching, and see you at the next video.